Okay, let me get the Zoomer screen share going. Then we'll all be on the same page once again. Okay. All right, can everybody see the screen? The screen share, I should say. Excellent, okay. Unfortunately, that means I have to move the Zoomers out of the way, so I won't be able to see you at the moment, but if you have questions, please just start talking. I think that will make it work. Because Zoom is still connected to the OWL, right? You check, double check that. Okay, cool. All right, cool. Okie dokie then. So one variable at a time. That's the catchphrase for the remainder of our session. Go. So once again, old stuff, new person, new software. I do want to start with just a few things that don't get taught in classrooms, like explicitly, in terms of how to work with data for the first time, because I've seen folks do things that took way more manual labor than was warranted, and I want to save that for you if I at all possibly can. So quantitative data can be stored in a variety of formats. It is not necessary for you to store your data in the software program you intend to use for analysis, and I actually wouldn't recommend it. In this class, we're going to import Excel files because you can look at them in Excel or in Google Sheets or whatever, and you don't have to have software installed like with you to be able to view them. So I find those to be easier to work with. I did look to see whether or not you could import JMP files into R. You cannot, but you can convert them to CSV, which then goes into R. So CSV is like a stripped down version of like an Excel file that has comma separated values instead. That tends to be a more lightweight version, like especially if you work with really large data, that's probably what I would recommend. But regardless of what kind of data you have, the process of getting data into a program such as R is threefold. We save it to a place, we get the address to that place, we find the path to the folder where it is saved, and we stick it in the right spot in our program. That is known as setting a working directory, and most software packages work that way. And then we would write and execute syntax to import the data into the program as a native format, meaning like it's then an R data file, or it would be a SAS data file. And the benefit of doing it that way is that your original Excel file is safe and sound on your directory. Like you can't accidentally overwrite it or delete it or mess it up. You can in SAS, interestingly. Like if you have SAS data sets saved, yes, that face is correct. You have SAS data sets saved, you can accidentally like ruin them from inside the program. Been there, done that, got the t-shirt. So we're going to work with Excel to keep things safe and sound, and because I'm guessing that since most of you, not all of you, but haven't used R before, you won't have data stored in an R format, because why would you? When you're entering data, like my Scratch, there are a few things you can do to save yourself hassle later. Use spreadsheets, it's totally fine. Just keep in mind that whatever formatting you use in spreadsheets to make it visibly easier to work with or more appealing will not transfer. So for instance, I see people that like, oh, if the cell is colored yellow, it means this. I'm like, nope, it does not. If it's underlined, it means this. It does not. Like you have to be explicit in terms of what you're trying to say about the data. It has to be codified in some kind of way that the program can read. If you are going to have variable names, they go in the first row and the first row only. Otherwise, this will cause big problems. Do not use special characters or spaces. Underscore is okay in almost every program that I know of, or dot is acceptable in R, but not necessarily in other stats programs. Use only as many characters as you need to keep it unique, because you're going to end up having to type these variable names in the code. So if you have a 32 character variable name, you're going to hate yourself for that. In other packages such as SAS or SPSS or Stata, probably JMP as well, variable labels are a thing. That's another field that is attached to the column in your data set that has a longer explanatory title that prints on the output, which is really nice. Yeah, R doesn't do that. It actually will mess things up if you try to add variable labels. So what I end up doing is just writing them as comments in the syntax files, meaning like notes to yourself that the syntax doesn't read as part of your own documentation. You need to start with a letter and not a number in almost every software package that I know of. And if you have a series of related variables, you want to name them that way. So for instance, if you have a stress scale with 10 items, you would not want to use words like worry, anxiety, fear, or something as like the stem, because you can't collect those in an easy way. Whereas if you say something like stress 1, stress 2, stress 3, then you can refer to that as a list to do things with. Like you can add across those columns, or you can move them all to a different place in the data set, things like that. If you are going to store information about groups, please don't use text. I know that's the most intuitive thing, but humankind is unlimited in the number of ways it can spell things wrong. And most of the time, string variables, or text variables as they are called, are case sensitive. So for instance, if you indicate that person 1 is in the control group lowercase, that is not the same thing as control group uppercase. So if you're entering data, that is a recipe for disaster to allow people to enter the text that they want. I know that in like Excel and other packages, you can limit, like you can make drop-down menus, like there's only certain choices. I would do it that way if you're working with people who need the labels. Otherwise, like control group is 0, treatment group is 1. Storing it as numbers is going to be a lot more fail-safe. If you want to add value labels, which is then a representation of how the number maps onto the label that you intended, that's a great thing. R doesn't do that either. You have to turn them into strings. So you would start with numbers and then turn them into strings. The convention that I follow, though, is to put the number that the variable label represents as part of the title, because it otherwise will reorder it, numeric into alphabetical. So for instance, if 0 is the control group and 1 is the alternative group, if you just write control group or alternative group, alternative is first. And that will screw you up because alternative is not 0. So if you tie the number to the label, that can save you some headache. If you have something like pick a number, 1, 2, 3, 4, 5, or other, don't put that in the same column, because then all the 1, 2, 3, 4, 5s turn into text and you can't work with it. So if you need, like, if you don't have if the answer is not applicable and you need an other, build a separate text column for that when you're doing it. And in my humble opinion, missing data codes are garbage. Don't do them. Like people feel the need to enter like -99 if something is missing. Don't, leave it blank. You don't need them. And I have seen students who in their initial assignments on their data turn in descriptive statistics where the minimum is -99. It gets treated as a number unless you override that to set missing data codes. So to avoid all of that headache, just leave it blank. It's missing. If you need to keep track of different reasons why something is missing, like didn't want to answer versus didn't show up that day, that's a separate column. And then you would have numeric codes that would go along with all the possible reasons for missing this. Dependent data. This is what I've seen folks struggle with this. You don't have to have one data set. If you have a complex sampling design where you have multiple kinds of units, so for instance, if you have schools that are nested within districts, that are nested within counties, or students that are nested in classrooms that are nested in schools, you can build a school level data set that has school level information, a classroom level data set that has classroom, and a student level data set. They can be 3 separate data sets, and that's how I would do it, because you can merge them all back together at the end. And once you do that, the higher order units will paste all the way down for the replications. So like if I have student 1, 2, 3, 4, 5, when I merge in the classroom information, it will get pasted across all the students because it's a constant for them. And then when I merge in the school information, the same thing will happen. It has to be complete with respect to each row. And you may think that this is somewhat obvious, but I once had a student who spent her entire summer break manually doing this in Excel, dragging the values down for the same unit in terms of the higher order characteristics. Don't do that. That is one command, a merge command in software. You don't have to do it manually. I, as a graduate student, once spent 6 weeks doing a data transformation manually per subject that I learned was 2 lines of code subsequently. So there's a lot of things that look like I can't figure out how to do this, that software has anticipated. So if you're ever in that situation, send me an email. Tell me what you're trying to do, and I can help you at least figure out the right words to search by, or maybe even have an example. So if I have people from different countries, for instance, I would have a person level data, country level data. In longitudinal data, oftentimes you have things that are collected per occasion, but then you also have things that are baseline characteristics about a person that you answer only once. So you would have a person level data set with a person ID, a time level data set that says which occasion it is from which person, then you can merge them back together, and the person's baseline information will be pasted across all of their occasions, as it should be. So these are the kinds of things that can trip people up if they're not thinking about it from an analysis point of view. All the rows have to be complete. In terms of the kinds of variables that we work with, the overarching umbrella that you have to recognize is that variable categorical or quantitative? These are my names. Because I just told you to store everything as a number, right? Don't use control group, use 0. Don't use treatment group, use 1. That then requires on the back end recognizing whether that is really a number or just a label. So this type of taxonomy of categorical versus quantitative guides 2 different processes: how you would summarize that variable and its salient features, and how we'd use it in an analysis. And I'm guessing what follows you would have learned at some point as levels of measurement, is how that's taught in an introductory material. I'm focusing more on how to use them in an analysis kind of perspective, which is related, but not quite the same thing. So I will say that on paper, it looks like your first homework assignment is going to be reviewing univariate descriptive statistics. Breaking that down, univariate means 1 variable at a time. Alternatively, you can have bivariate, which means, can you guess? 2. And multivariate, which means a lot. Yeah. So univariate is the type of analysis that we're going to be doing, predicting 1 variable at a time. Descriptive means we're not trying to make any kind of conclusions. We're just trying to say this is what happened, this is the mean, or this is the proportion of people in this category. And statistics, meaning we're dealing with the sample that we have that we hope applies to some theoretical population, but we don't have access to it and there's no way of knowing for sure. The actual purpose of homework 1, though, because these are all things that I'm guessing you've seen before, is to use familiar ideas as the basis for getting started with R. I will say, students in the past have used the software they already know to do homework 1 and done it successfully, right? If you know how to use JMP, you can do homework 1 using JMP, but that kind of defeats the purpose. The idea is to get you started in R with something you know how, like you know what it means, like you know what a mean is. So I'm hopeful that you can take the resources that I'm putting together and start to get used to doing R. And homework 1, in terms of the website, the homework portal that I showed you earlier, you're basically completing a method section. That's the idea, is how would you describe your sample with respect to the variables in the analysis. So categorical, then. The numbers are not numbers, they're labels. There are 3 main kinds that you will see in life: binary, nominal, or ordinal. Are these familiar terms? Cool, all right. So one thing I will point out, binary and dichotomous are not the same. They are often used interchangeably, but binary means specifically 0 or 1, whereas dichotomous means 2 choices. If you have a variable in which there are only 2 possibilities, most folks would store one of them as a 0 and one as a 1. There's nothing wrong with storing them as a 1 or a 2, but when it comes time to putting that into an analysis as a predictor, you're going to need to make it 0 and 1. The reason for that, as we'll discuss, is the interpretation of your intercept will be weird otherwise. Not wrong, but weird. And some things in life, there are only 2 choices. Nominal is a word that refers to unordered categories, such as your favorite type of pet, ice cream flavor, what degree program you're from, and so forth. You might store those as 1, 2, 3, or 4, but the numbers are not really ordered. They don't have meaning in terms of amounts. Ordinal is the tricky one. People want to think ordinal is numbers, but it's really not. So this is very, very common in the social sciences, especially for self-report data. you might complete a scale in which you are asked the extent to which you agree with something, with choices ranging from 1 to 5, for instance, strongly agree, neutral, disagree, strongly disagree. And equally ordinal choices would be 1, 20, 300, and 4,000 rather than 1, 2, 3, 4. These aren't numbers. People want to treat them as numbers, but they're not really. And so that one gets a little tricky. One of the things that I want to show you this semester is an empirical way by which you can ascertain whether it's okay to think of it as a number or it's not. I'll foreshadow that. If you wanted to put an ordinal predictor into a regression model, you saw regression at the end of this first semester, right? So you're building a line, essentially, where you're relating an X and a Y, and let's see, it goes this way or this way. I'm very bad at doing it from this way. There we go. That's positive, that's negative. There we go. If you draw a line through an ordinal variable, another way to say that is that you are saying the difference in the outcome between a score of 1 and 2 is the same difference as between 2 and 3 as between 3 and 4. Like, you can think of them as like little mini lines that you're like stitching together. Well, I will show you a way to test whether the slopes of those mini lines are sufficiently comparable to where you can say, yeah, just one line's good enough. And if that's true, then 1, 2, 3, 4, even though it's not really a number, may be good enough with respect to the data. Otherwise, if the mini lines don't agree, you're going to lose information and introduce inaccuracies by treating it as a number. So it's not really a question as to whether it's interval, it's a question as to whether there's a linear relationship that underlies the differences between the categories. That's it. And synonyms for categorical: a discrete variable, a grouping variable, a qualitative variable, and in R they are called factor variables as well. All of those words mean the same thing. What I would like you to hang on to is binary versus nominal versus ordinal, because that will dictate how they go into the models. And in advanced coursework in which these kinds of variables are outcomes instead, things to be predicted, that also, the type of model depends on what kind you have. Quantitative, then, is the word that I use for numbers that are actually numbers, amounts. In other words, interval measurement, where we are assuming the distances between means something. Most quantitative variables that we see in practice, though, are not actually continuous. They have boundaries: 1, low end, high end, or both. For instance, a binomial type of variable is the number of occurrences out of a number possible, such as number correct on a test. What's the worst you can do? 0. What's the best you can do? All of them. And if you compute that as a percentage or a proportion instead, the same is true. If it's a proportion correct, the worst you can do is 0 and the best you can do is 1. So it is a number. And differences between them mean something. Like, I got 1 more right than you did means something, regardless of whether I got 37 right and you got 38 right, or I got 18 right and you got 19 right. Like, those all mean the same thing. But when predicting these kinds of variables as outcomes, we start to run into a problem. Because a line, right? A line keeps going. The line would predict that you can get 110% correct at some point, right? Or that you can get negative 10% correct. So when these variables are outcomes, we have to do something to trick it into understanding that, no, you can't go past the boundaries. That is a family of models called generalized linear models, if you've heard of that. I teach a whole course on that at Iowa. That is normally the follow-up to this course, what we used to do, because it's linear regression with extra stuff added to it to make it stay within the boundaries. Functions with boundaries are count data. The count of events, number of absences that a student has, number of cigarettes I've smoked today, number of drinks I'm going to have as I cry over my tech that doesn't work, those kinds of things. Like, what's the lowest count that you can have? 0. I'm not going to have any drinks, I'm not going to throw any fits, and my kid's never going to be absent. That's the best I can do. What's the worst I can do? Positive infinity. So in these kinds of outcomes, it would have to understand that it can't go below 0, but it can go all the way up in the other direction. And by the way, some additional terminology that you may come across: special cases of counts. Sometimes there are no zeros that are possible. For instance, if you are working with archival data, say from a hospital, and you are studying the number of days a patient has to stay, well, in order to get in the data set, they had to be in the hospital. So they were there at least one day. There's nobody who's going to have a zero. That is what's known as a zero truncated count. Another situation that is very common is when you have a mixture of people who do or do not do a behavior. The people who do not are always going to be zeros. The people who do could be a zero because they haven't done it yet, or they could be some non-zero. And that is what's known as zero inflated. So that is another type of outcome in which you're trying to predict the probability of being a zero and then the amount if you're not zero. So those are sort of advanced concepts. I just want to set the stage that non-continuous numbers have models to predict them too. Okay, so quantitative variables that are continuous, that means unbounded. I honestly cannot come up with an example of what would truly be a continuous variable in the social sciences. So in general linear models, our outcomes, the things we're predicting with the model, are supposed to be plausibly continuous in interval. Most of the time, though, we just sort of pretend, like, it is good enough. Otherwise, you need a different family, generalized models, as I mentioned, that are situated for variables with boundaries. But the key word is plausible. So I will introduce you to a vocabulary word that I made up, continue-ish. That's what we usually have. It's not continuous, it's continue-ish. And no, please don't write that in your papers. Like, that's not a real word. But I think it's useful in terms of thinking about, well, this is close enough. So examples, something called ordinal treated as interval. If I have a one-item survey on a scale of 1 to 4, how do you feel? Most people will be like, yep, that's ordinal. That's not really a number. No. What if I give you 10 items, each on a scale of 1 to 4, and you come up with a sum? Oh, well, that's a number, right? Not really. People will treat it that way. So in that case, you have an outcome that varies between 10 and 40. If you have 10 items, each on a 4-point scale, it has 2 boundaries. So it's really not different than a binomial outcome. The same thing is true if you take a mean instead, which you should always do if you have any chance of missing data for your items. Then the range is 1 to 4, continuous between, but you still have those boundaries. That's something to watch for in the data that you're going to be analyzing. Continue-ish, other examples, response time. So in cognitive psychology, which is where I originated from, response time is a very common outcome to measure cognitive and attentional processes, like how quickly can you do this? What's the fastest we can be? Some lower bound of like biological function, maybe 200 milliseconds or something to click a mouse, something like that. Eye movements happen even faster, but there is a lower bound at 0. Latent trait estimates, is that a vocabulary word you've heard before? Probably not. Latent variables, latent constructs, true score. Like if you've had any sort of measurement or test theory stuff, how many of you had to take the GRE to be here? Or an MCAT, or other kinds of standardized tests that people use to make decisions. Those are latent trait estimates. They're not required in a lot of places anymore, and I think that's actually a good thing because I don't like them. But that's a whole separate conversation. But they have boundaries. They're not continuous either. Like the GRE, I think, ranges from what? They changed the scale. Like 150 is the middle, I think, 110. What is the scale of it nowadays? You know?
170 is high.
170, okay, yeah. So they have boundaries, right? But that's something that people predict as continuous, even though I think it varies in units of like 5 or 10, something like that. So continuous is everywhere. I really I can't think of a single example that's truly continuous on both ends of variables that we would work with in the social sciences. Then there's also ratio. You're never going to see this, not unless you're like in the physical sciences where these things exist. So I wave my hands at that and say, yeah, you can think of it as just, it's a number that means something. All right, how are we doing, folks? Hanging in there? Questions? Let me flip back over to the Zoomers. There they are. How are we doing, Zoomers? Zoomers and Roomers.
Okay,
Yeah, hit me.
I one other project that's sort of focused on some like using survey data. And I guess I'm wondering, like, is it going to be outside the bounds of this class to sort of like part reasons us like figure out language. But like to predict the probability over time that someone responds either a 0 or a 1 to a particular action.
That will be something I talk about in the very last week, but not something that we will have a chance to do like in homework or any of that. So yes, technically out of bounds. I can point you towards resources though.
That'd be great.
But I know it's going to be covered in the other section of regression, but the way that I do it takes a whole month.
That's good.
Well, it's another framework thing. So briefly, it requires something called a link function, which is a transformation of the outcome to be predicted to put it back on a scale that is truly continuous. And the scale that is used is something called a logit or a probit. There's several of them. And what happens is you take the probability of the event divided by the probability of not the event. That thing is created as odds. That then varies from 0 to positive infinity. If you take the natural log of that thing, then it varies from negative to positive infinity. It's truly continuous. That's called a logit or a log odds. So your regression model predicts log odds because then the line can keep going, right? No problem. But when you back translate the log of the odds of the probability, the probabilities stay within boundaries. And so what ends up happening is that line that's straight when predicting logits, if you convert it into probability, like as a y-axis, it's a bendy line, like an S-shaped curve. So the short answer is yes, the same concepts will apply in terms of how we build models and evaluate their effects, but there's that extra step that has to happen in logit land. The other thing that has to happen is that because the outcome is not continuous, a normal distribution can't ever be viable for it. Like there's no way to take two possibilities and spread them out into something that looks like a bell curve. That's not going to happen. And there's no data transformation in the world that will make it so. But good news, we don't have to pick normal. There's literally like dozens of distributions that match different kinds of data. And there's something called Bernoulli that matches two categories. And if you have multiple trials of that, such as proportion correct, number correct, then that is binomial. And counts have something called Poisson or negative binomial. So it's like Mr. Potato Head. Do you guys know what that is? Am I dating myself? So Mr. Potato Head is a toy where there's just like holes where the eyes and the nose and you like stick body parts in it, and then you can like stick an arm where the eyes go and it looks really funny. It's kind of like that. Like you have this Mr. Potato Head and it's like, well, normal doesn't fit. I'm going to go grab this and put it in here instead. So it's like plug and play.
But
yeah,
those all words are familiar, and I think I can definitely understand them. So I'm glad what I was reading before this is not. Thank you.
It's like this is the core, and then we got to add those pieces to it to make it work for two outcomes.
What if at the unit I don't know, sorry, but if like the unit becomes like a school, and then it's like percent of students who did a 0 or 1, does that then fall within sort of generalized?
That's eyes. Okay. So that also uses a logit because you're predicting something that goes between 0 and 1.
Yes. Okay.
Not just 0 and 1, but between. But it's the same idea. Probability has a S-shaped curve to shut it off. And then, but you need, because it's not just two choices, you need a different distribution. And so that one, I would actually hack binomial and add some pieces to it. But that has a distribution, like set of choices that go with that kind. Yep. My previous class, let me pivot here for a second. Am I sharing just the application or am I sharing my screen? I think it's, okay. So you can't see my website. Okay, got it. On my website, if you ask the Google for lisahoffman.com, you will find me. That was actually a birthday present from my husband, because that's what nerds get each other for presents is domain names. And on my website, I have a tab called Course Materials, and all of the courses that I've taught, the most recent versions are there. You're looking for something called 6270, which is generalized linear models. And all the stuff that I just said is there.
But you have intent from teaching that.
I would like to.
Okay.
So we were hired to help grow the training and presence of quantitative methods. But it's a chicken or egg thing because we don't have enough students who want to keep going. So I'm in full on recruit mode right now. So like if you can get enough people who want to take generalized models, I can teach it. You're here?
Yeah.
Yeah.
I'll take all.
Yay, math. Exactly. Yes. I'm here for that. No, I have, at Iowa, I had a rotation of 6 different advanced courses that I went through. And my husband has additional ones too. So he's teaching a course this semester that's designed like as a next one for this, and that's one of the units in it is generalized models. Yep. So yes. Thanks. Did I answer the question?
Yeah.
Cool. Keep the questions coming. Please do. All right. We're switching gears then, unless there's other questions. I especially like the how does this apply to me questions, because a lot of you have similar kinds of data. Like percentages is a very common thing, like percent proficient as an outcome or whatever. That is very common, like I said. All right, I want to pivot a little bit and introduce you to our syntax, just like conceptually. And I will preface this by saying everything I'm about to say, I'm going to walk you through in a video in front of R. So this is just like, you'll hear it one time, you'll hear it again, because no one learns everything perfectly the first time through. Cognition does not work that way. The most important thing to recognize is green text. Green is magic. That is how you indicate comments to yourself. And in our code, the magic button that indicates it's a comment is, depending on how old you are, either a pound sign or a hashtag. Take your pick. To me, that is a pound sign. If you type that first, then R will disregard whatever follows, so you can leave yourself a trail of breadcrumbs as to what you did and why. And future you really needs this. It's not enough to just like copy what I did, because when you come back to it, it won't make any kind of sense. R is composed almost entirely of functions. If you have a programming background, you're like, okay. And if you don't, you're like, why are there so many parentheses? This is weird. That's how it works. So R is composed of base R, which is like the people who made R made certain functions. And the one we're going to use in this class is called LM, stands for linear models, is a base R function. It works great. I have no complaints about it. Then there are user-created packages that do specific things that are filled with their own functions. And that's where it gets a little dicey. If you are ever looking for documentation, if you come across an R package in someone's work and you're like, oh, what does that do? Google the name of the package and put CRAN with it. Comprehensive Research Something Network is what it stands for. If the R package is good enough, it gets to be on CRAN. But a lot of times what I have found, because you have to go through certain checks to make sure it works on different operating systems and stuff like that, I have found though that like someone writes a package and I go look for it and CRAN took it down because it broke too much and people complained, and then you can't find it anymore. So that's also an indicator that maybe you don't want that package because CRAN doesn't like it anymore. So for example, this is code in R to download, install, and then load, meaning bring into active working memory, 2 different packages that we're going to use. One is called read Excel. Can you guess what that does? Reads Excel files. The other is called psych, which stands for psychology, because the guy who wrote it, Bill Revell, is a psychology professor at Northwestern, so he called it psych. And if you look at this, it's sort of readable, but it's not something you would ever produce. So if, note the blue, that's like a programming command, not require, like the thing here, like if it's not there already, go get it and install it. And then semicolon separates that idea, and then there's a new idea after it. Library means bring it into focus. So it's not enough to install things. You have to bring them into active memory for R to know what to do with it. So once you've already installed a package, you don't have to redo it. But the first time you guys open R and you run this, your output is going to be like all these words as it goes through and like loads everything. It looks a little scary. Don't be afraid. That's only one time though. So it can take a bit to open R and get things installed the first time, but once it's there, then you just have to load it and it goes much faster. So in this little snippet of code here, you'll see the hashtags in the green. Like this is my note to myself as to what the code below is doing. And then within each of these, I have a note as to what that package does for me. so I can keep track of the packages and what I had intended when I downloaded them in the first place. First thing we do is set a working directory. Tell it where to find your stuff, because then it will go there first, and when you output things, it will send them to that place. So you want to paste inside the quotes, the path to the folder where your stuff is. And if you are a Windows user, the slashes are backwards relative to what they are in Windows Explorer. So that's one hiccup. For Mac, they look a little bit normal. So for instance, the path, I use Dropbox. 26 is the year. This is the class. That's my naming convention. And this is stuff that's going to be in lecture 1. So that's the folder on my computer where stuff is going to go. Next step is to read in data. In R, you can have multiple data sets open at the same time. This is both good and bad. It's good in the sense that it allows a lot of flexibility in doing data manipulation and merging kinds of things. It's bad in the sense that anytime you write a command, you have to say which data set you're doing it to. So you got to get used to that. So this package right here is saying, make me a new data set called example1 from this function, read Excel, that was from the package here. Here's what the path is called, the file is called. So I am using for this the General Social Survey from 2012, which was featured in a textbook that I used a long time ago. Within Excel, I want to tell it what the name of the sheet is, and I want it to read the names as variable names. Note what is case and space sensitive here. So uppercase data for the D is not the same thing as lowercase data. And the error messages you get are almost incomprehensible most of the time. You would not figure this out necessarily, other than through trial and error. The other thing is that when you import data, there's no guarantee it's going to be the right format for analysis. Sometimes it is, sometimes it's not. So I've gotten in the habit of using this additional command to turn it into something called a data frame, which is what we need it to be. So example 1 has been converted into the right kind of data set for us to analyze if it hasn't already been there, this step. So the syntax itself, I want to describe the structure and then give some examples. So for example, imagine that you were asked how your dinner was and you want to say, it was fine, it was not too spicy, which is a good dinner for me because I have a Midwestern palate and I do not like anything spicy. So an example would look like this. And if you just stare at this, it's like, what? But they're arguments within functions. So let's break this down piece by piece. My answer is the name of the set of results that it is creating and storing in the environment. It's going to have all the numbers that show up in front of you, sometimes buried, you have to search for it a little bit, but it's there. The saved results do not print by default. You have to ask for them. So most analyses will be followed by summary, which means print the thing I just did, please. So my answer is the object I'm asking it to print. The function that it's using is answer, and I decided to be a little clever with this because people like R puns. So capital R for R. The name of the data set is data equals, my data set is called dinner. Inside, the rest of these are arguments. So for instance, spicy would be an option that I could set to either true or false. Your model itself starts after the word formula. So equation, you can think of it that way. And note this little thing here, that's a tilde or a squiggle mark as I call it sometimes. That's because equals was already taken. So rather than equals, they have this thing. So response would be the outcome you're predicting. On the other side of the equals will be the predictors. So tips for effective syntax, you want to build lots of comments and give yourself sort of signposts to logically group things. So for example, this is an overview of what example 1 looks like from in my R file. I have this little block here that says like what happens underneath, and then this block delineates then a change in what's happening. So when I scroll quickly through it, it helps me locate different things. And you'll see this a lot in terms of how I organize my stuff. All of my syntax files are going to have this structure right here. Start with output display, load the packages, set the directory, import the data, make any new variables I need, open up an external file to send output to. That way I can take it with me and not have to rerun things, whatever commands, and then close it. And this is the type of structure that you will get for each homework. Like I will set this up as a template and you just fill in the pieces. That way you don't have to fight with R. So for now, we focus on what kinds of features we would need to describe different kinds of data. Differences among categorical variables are always going to matter. Differences among different kinds of quantitative variables, whether it's continue-ish or us, that matters more when it's an outcome. So categorical, all you need to know is the frequency per category, the end. That's the only thing that's relevant. And in most cases, it's more understandable to express it as a proportion, so the frequency divided by the total. This I see confused a lot. Proportions range from 0 to 1. Percentages range from 0 to 100. So you have to be careful. Like if I ask for a proportion as an answer, don't put in like 93.6. It won't like that. It would be 0.936 instead. And we can display this with a bar graph. I'm guessing you've seen those. So this is an example of what it would look like in terms of table as the command in base R. So I'm on slide 19 here. Print is how you can put just text in your output. So those are like notes to yourself as to what the numbers below it mean. Table makes a table. X equals is what would you like tabled? And note the dollar sign here. The convention is that the first part of it is the name of the data set. Then the dollar sign separates the name of the data set from the name of the column in the data set. And if you can't remember that, just think to yourself, if I learn R, someone will pay me. And that's what the dollar sign is for. So this is the output that this little command would generate. I have a variable for marital status in which there are 5 choices. It spits out the number of people in each choice. If I want to convert that into proportions, I can take the same table command that's on the inside here and stick it inside another function called prop table that takes those frequencies, divides them by the total to create proportions. So it's like a function inside a function inside a function. That's why parentheses are really important. One of the nice things about RStudio, which is the graphic user interface for R, is that if you're off, it will put a red like angry mark next to it. So that's your clue that you've missed either a comma or you're off in terms of your balance of your parentheses. Here's a picture, bar plot. So you've seen pictures like this before, I imagine. For categorical variables, this is just fine. So this is how I created it, a table to work with the labeled version of these. So these are actually strings that it's tabling. There's a height command that works with that. And then you can stick the whole thing into prop table to create percentages instead. And base R has graphic functions that do basic things. There are other advanced packages called ggplot or ggplot2 that make fancier graphics. We're not going to get a chance to get into too much of that, and I don't, I haven't used it very much, honestly. I don't do a lot of graphics in R. I prefer to do it in other packages, but that's one of the things I'm going to work on this semester. So what about quantitative variables? These same types of tables are not going to be useful. So this is a summary from a different package because I like the way that it's output. Income is a variable that's also in this data set, and here are the choices. So we can see right away this is continue-ish. But we also don't get a sense as to what the distribution looks like because it's treating each of these distinct values as its own thing, and they're not in relation to each other. So this type of bar plot is not a good summary of a quantitative variable. Instead, we can do something called a histogram, in which we essentially arbitrarily bin these things, and then we can get a summary that better characterizes the data. So if you were to look at this summary of income, do we have a lot of rich people or a lot of poor people? Would you say, if this is income in thousands, or poor people? But if I looked at the previous picture, I'd come to the opposite conclusion, because there just happens to be a lot of people at this point, but the numbers on the x-axis are not scaled in an interval way. So bar plots don't work for numeric data, histograms do instead. All right, it is 7:15. I am thinking that this is probably a good place to stop for today, since I promised I wouldn't go the whole time. And it's 7:25. I will make a video at home to finish this up. I will let you know when that is available, as well as the video demonstrating how to do this stuff in R, actually running things, as well as the homework system video demonstrating how to do that. Because I'm not going to see you for 2 weeks, so I got to give you some stuff to do. that seem fair? All right. Questions or comments before we adjourn then? All right, I will hang out for a few minutes in case people want to talk to me. Otherwise, go have your non-Midwestern dinners and enjoy your evenings. Thank you very much for your patience with the tech. I promise I will fix it. I have 2 weeks to work on it. Thanks for being here, folks. You too. Bye for now.